Hello everyone, in this tutorial we're going to use to read and process a JPEG file to extract stars' positions and their features. We're going to use also astronomic formulas to estimate features as wavelengths, temperature, distance and other criteria. So if you look in this picture, to work with a JPEG file we need to read it using an OpenCV library. The JPEG image extracted would be a form of three-dimensional arrays, of a three-dimensional array made of three layers, better said. The first layer being the red channel, second layer green channel, and the third blue channel. Of course, the correct arrangement is blue, green, red, but then we need to flip it into red, green, blue. So what we get is pixel values on XY axis that are two dimensions, and the third dimension is the layer index 0 for red channel, 1 for green channel, and 2 for blue channel. Of course, after rearrangement. Okay, so as you see, this is the red channel, the green channel, the blue channel. Combined together, these three layers of the three-dimensional matrix combined together would give us the JPEG image that we see on top. Contours detection. Using OpenCV library, we will at first use a Gaussian filter to smoothen the image in order to clear the noise and spec details, of course. After that, we detect the contours of the stars, and by writing x indices, y indices equal np.where galaxy contours ::, 0, for example, we can get the XY coordinates for all the stars, mainly located, of course, in the red channel. If we do it for, instead of 0, 1, you get the constellation or the contours for the green channel and 2 for the blue channel, respectively. By using X and Y indices, which are the coordinates for all the stars detected within the image, we can use one XY tuple, which would be the coordinate of one star, to perform measurement on one of the stars to get different important parameters and perform measurements. Parameters such as brightness, luminosity, some is extracted and some is measured or calculated, of course. Okay, conversion of color to wavelengths. Now, as we know, each wavelength has a specific color unless it falls beyond the visible spectrum, whether infrared or ultraviolet, at least from the vantage point of an ordinary telescope. So the relationship between RGB values and wavelengths is the following. You have for pure saturated red a wavelength ranging from 620 to 750 nanometers, 750 being the peak, which is the maximum for red 25500. Same concept for the green. For a green channel, the corresponding wavelength would be 495 to 570 nanometers, the latter being the maximum. And for the blue channel 00255, it corresponds to 450 to 495 nanometers wavelengths. So how to get the wavelengths of a mixed channels image, which is often the case. You often see an image with mixed values for RGB. So for the conversion of color to wavelengths, this is the function that we need to write. You need to get the ratio of RGB values within the color. You divide it by the maximum, which is 255 for the three channels, and then you multiply the ratio, each ratio by its corresponding maximum, of course. So R divided by 255, you multiply it by the 750 nanometers, which is the wavelengths. So you get the ratio of each color on the three channels, whether red, green, and blue. At first, we need to get the ratio for each channel, meaning that the red ratio is the value of red within the color vector that we have divided by the maxima, which is 255. Same thing for green and blue. And then we multiply each ratio by the maximum of its corresponding wavelengths. So R divided by 255, we multiply it by 750 nanometers. We add up the green ratio multiplied of course by 570 nanometers corresponding to the green, plus blue ratio times 495 nanometers, and we add to all of that the base wavelengths, which is not visible within the pixels, usually corresponding to the infrared, which is the value 380 nanometers. Finally, we return the answer, of course. Conversion of color to wavelengths: red corresponds to 620, 750 nanometers, green corresponds to 495, 570, blue. Okay, so we have an example, a color of 121, 30, 78, respectively RGB values for that color, for that pixel. So wavelength would be 380 nanometers plus 121 divided by 255 times 750 plus 30 divided by 255 times 570 for the green plus 78 divided by 255 times 495 nanometers, and you get the total value for that. Okay, measuring star temperature. So to measure the star temperature, we need to use the following equation. An important factor to be integrated is the Wien's displacement constant, B equal 2.897 times 10 to the power minus 3. Temperature, Tk, equal B divided by lambda, B being the Wien's displacement constant, and lambda, the wavelength, needs to be converted to meters, because the value we get for the wavelengths from the former function is in nanometers. So we need to convert it to meters to get the temperature of the star in Kelvin. Total energy of the star. To get the total energy, we need the Stefan-Boltzmann constant, which is 5.67 times 10 to the power minus 8, denoted as sigma, watt meter minus 2 by Kelvin to the power of minus 4. So energy equals sigma multiplied by temperature to the power 4. This is how you get the total energy of the star. Of course, other factors will depend on the brightness as well. Okay, now to get the distance of a star, the distance is related to the brightness. So what we look for is the brightness decay, the decay of brightness, meaning that as a star gets further and further, its glare, its brightness decreases. And this is the ratio we look for, which happens to be inversely proportional to the square of the distance. So as brightness decays, d, or the distance, is raised to the power of 2. The distance is up to the second power. After that, we can get or measure the luminosity. Now, luminosity depends on brightness. Brightness is taken from the number of pixels surrounding the star on a specific radius. You get the maximum or the average brightness for those pixels. So L equal brightness times 4 times pi d square being the distance to that star. Luminosity equal brightness times 4 times pi d square. Now, also we need the Stefan-Boltzmann constant to get the radius and measure the area of a star. So the star radius is r equal square root luminosity divided by 4 pi sigma, which is Stefan-Boltzmann constant, times temperature to the power of 4. Then the area equal pi times r square. In this example, we're going to work with JPEG images basically. The JPEG image that we're going to work with belongs to a nebula within the Milky Way. So, and I have provided the link in the description below. Let's upload this image. I'm in Google Colab right now. You press on Files. You go to the image and simply drag and drop. Alright, the image has been uploaded. Now we need to use a library to work with this JPEG image. The library which converts this image into a 2D array and helps us process it is OpenCV. We need at first to install it. So in order to install it, pip install OpenCV-Python. And let's also import CV2, import numpy snp. Okay, let's run it. Now, in order to read the image, galaxy m equals cv2 dot image read or mread, and the name of the image, which is milky-way dot jpeg. milky-way dot jpeg. Let's check the shape of the image. Galaxy m dot shape. And you notice something. Since it is a JPEG file, it has 3 layers basically. 853 pixels height by 1280 width, and 3 layers for the 3 channels. 3 color channels of the JPEG image. We have respectively green, blue, and red. This is how it is coded into the Galaxy image variable or matrix. Now, to visualize the image, we simply import matplotlib .pyplot as plt, plt.mshow galaxy image. And you have a very rich image with details. Of course, you definitely have noise within the image, but you have thousands of stars. Okay, the next thing I need to do is convert from GBR to RGB, the layers being red, green, and blue, rather than green, blue, and red. In other words, if you go back here within the shape of the image, the first dimension, which is 0, is for green, the second is for blue, and the third, which is 2, is red. I need to rearrange them into red, green, blue, respectively. Galaxy RGB equal cv2.convert color galaxy image cv2.color blue, green, red to red, green, blue. Okay, so we need to convert from BGR to RGB. After that, we need to get the grayscaling for that image. Okay, what we're doing here is writing a function that will get the contours for different stars within this image. Blurred equals cv2.gaussian blur gray 3x3, which is the filtering factor for noise for this function. The edges is equal to cv2.canny blurred. Blurred would be the confines of the blurring for the contours. 30 by 34, or let's do it 40 by 150. Okay, the blurring area, so to speak. Find contours in the edges. Contours hierarchy equals cv2 dot find contours edges cv2 dot retrieve external edges, meaning cv2 dot chain approximation simple that reconstruct the chaining, the hierarchical chains of different contours. Galaxy contour equal galaxy RGB dot copy to move it to a new image, to draw the contours to a new image instead of the old image, of overwriting the old image. So cv2.draw contours, galaxy contours, contours array -1, 255, 255, 255, meaning on all the colors. RGB 1. Okay, 1 is the scale of the contour. This is how many pixels would be. Display the image. with the contours plt.imshow galaxy contours. Let's look at it. Oh, we did a typo. Okay. It was missing a comma. Now, looking at the picture, you notice we have thousands of stars that have the contour around them. So we're getting, after that, the XY indices for these contours that have been plotted over the image, that have detected the location or the positioning of the stars. So by getting X and Y for different contours, we can get the coordinates of these stars. XR, YR indices belong to the red channel indices for the stars. Of course, we have a mixing between different channels. So one star can have all different channels within it. Okay, but here you notice we have galaxy contours. Get me everything on XY on the red channel, which is the 0 channel, the third dimension. XG, YG, the same thing on channel 1, which is the green channel. Okay, if we get one of the channels, like XR indices.shape, it will give me the number of stars, approximated number of stars for the red channel, which is around thousands. Okay, 106,000 stars, something like that. Okay, it may differ for the green channel, but we need to know that for the different channels, they are intermixed together. So some of the stars have the red channel dominant, some other stars have the green channel dominant. So here it is, the purely green channels within the indices, XG indices. Okay, it has, of course, a larger number of positions detected, so to speak. Import random as rand. Here I'm getting a random point within the indices array, a random star, so to speak. So XR indices, rand.randint, 0 to len of XR indices. So get me a random number from 0 all the way to XR to the width of the image in the X domain, and Y equal YR indices, rand.randint, also the same thing. Print XY. Okay, we've gotten a random point having X equal 170, Y equals 381. Okay, now we need to convert from RGB to wavelengths. As you see here in this image, the red channel corresponds to 620 to 750 nanometers, the green from 495 to 570, and the blue 450 to 495. So I'm defining a function that will get the wavelengths from RGB. Okay, at first I need to get the ratio of red, green, blue within this pixel. R equal R over 255. So how many of the 255, which is the max of any channel, we have in RGB domains? Wavelengths equal 380, which is the base, because you have the infrared that's not visible within the image, equal R times 750, which is the maximum of our channel, plus G times 570, plus B percentage times 495, which is the maximum of the blue channel. Okay, so B, which is the percentage or ratio of B, which is the value of B divided by 255, we multiply it by 495, return wavelengths. So let's check or test this function, star wavelengths equal RGB wavelength, and we'll get the wavelength of one of the stars, which is located at XY, that we've picked randomly from the function listed moments ago. So XY0, XY1, XY2, print wavelengths, star wavelengths. Okay, we did a mistake here. Oh yeah, we need to run the function back. So the wavelengths is equal to 430 nanometers. Okay, now from the wavelengths I can get the temperature, because we have lambda equal B over T, with B is the Wien's displacement constant, 2.0 897 times 10 to the power of minus 3. Okay, this is the value. Depth measure star temperature wavelengths. Temperature is in Kelvin, so B equal 2.897 times 10 minus 3. Temperature equal B divided by wavelength, return temperature. Okay, now we're defining another function, measures the energy, total energy of the star. Energy equals sigma times T to the power 4, with sigma is the Stefan-Boltzmann constant. Okay. So, define measure star temperature. Sigma equal 5.67 times 10 to the power minus 8, and we equal sigma times temperature to the power of 4, return energy. Also, we need to define the function to get the star maximum brightness. Image RGB, XY at a specific point, right? XY and radius, which is, encompasses the number of pixels around this area. Okay, so M gray equals CV2 dot CVT color, image RGB. So we've converted the image to a gray image, gray channel only. Image gray equal M gray, x minus radius plus x plus radius, which are the x confines of this circle, and y minus radius to y plus radius. So max equal np dot maximum M gray, the maximum value of all these pixels we've selected. Correlation factor is equal 10 to the power minus 6. Flux, which is the power of emission of light in this star, equal max times conversion factor. 0 point magnitude equal minus 2.5 times np dot log 10 conversion factor. Magnitude equal minus 2.5 times np log 10 flux plus 0 point magnitude return apparent magnitude. Okay, define. Now we need to measure the star average brightness. The same formula, but here we're getting the average value for the brightness. So in gray equals CV2 dot convert color from image RGB to the gray color. Okay, CV2 to gray. M gray equal M gray x minus radius to x plus radius, y minus radius to y plus radius. Average equal np dot mean, which is the average for M gray. Conversion factor 10 to the power minus 6. Flux equal average times conversion factor. 0 point magnitude, these are formulas by the way, minus 2.5 np dot log 10 conversion factor. Apparent magnitude equal minus 2.5 np dot log 10 flux plus 0 point magnitude, which is the base, the reference for the color value or the luminosity value for that pixel, and return apparent magnitude. Okay, now we have a relationship between the brightness and the distance of the star from Earth, from the vantage point of observation on the surface of the Earth. So B equal 1 divided by D square. Okay, this is relatively the formula. We need to import math. So define measure star distance, and the argument taken is the brightness. So we need to compare that to the brightness of the star, which is far 1.581 times 10 to the power minus 5 per parsec from Earth, 1 parsec being 2.38 light years, and the apparent brightness is 1361 watt per meter square. So brightness decrease equal brightness divided by 255, 255 being the maximum power of the pixel. Okay, we're considering it as the brightness of the sun. So distance equal math times SQRT of 1 divided by the brightness decrease. Okay, and return distance. So we defined the function that will get us the distance to the star. Now, another formula is apparent brightness equal luminosity divided by 4 pi distance square. So we can get from it luminosity. Okay, so define measure star luminosity argument is brightness and distance, both of them. So luminosity L is equal, of course, brightness times 4 pi d square. Okay, but the brightness we need to get it in watts. So brightness ratio to sun is equal to brightness divided by 255. Luminosity equal brightness ratio to sun. We multiply it by the brightness of the sun, which is 3.838 times 10 to the power 26. All of that, we multiply it by, okay, let's write a note here. Sun's brightness is 3.838 times 10 to the power 26 watts, of course. Okay, all of that we multiply it by 4 pi distance square, and we return luminosity. Okay, another formula is L equal 4 pi r square, which is the radius of the star, sigma, or Stefan Boltzmann constant, times temperature to the power 4. So define measure star area, luminosity, temperature, sigma equal 5.67 times 10 to the power minus 8, radius equal mat dot square root of luminosity divided by 4 mat pi dot pi sigma times temperature to the power of 4. The area is, of course, math dot pi times radius square, right? Radius to the power of 2. And return area. Okay, great. Now we've pasted all the functions that we will need, okay, to practice on that arbitrary point that we created, okay, that we found among the indices. So let's at first get the temperature. So temperature equal measure star temperature, wavelengths, star wavelengths, which we've gotten before, okay, and energy equal measure star energy. The argument is the temperature that we've gotten from the equation before it. So print, of course, the temperature is in Kelvin, so star temperature equal temperature K or Kelvin, star energy. Okay, as you see here, for the temperature, you know, the value doesn't make any sense, right? Because it is to the power minus 6. Okay, if we print star wavelengths, it is 430 but nanometers. It needs to be converted to meters. So we need to go back to the function, right? So wavelengths is in nanometer. So to convert it back to meters, it needs to be multiplied by 10 to the power minus 9. So wavelengths be divided by wavelengths times 10 to the power minus 9. This should fix the problem. So if we run it back, you would get the value, the new value for the temperature. And now it makes sense because the star temperature has become 6,731 kelvins, okay, which is a hot value, but it makes sense. Now, for the brightness, we need to measure the average brightness. So measure star average brightness, galaxy RGB, XY, and 4, which is the radius. The distance to the star equal measure star distance using the brightness and we need to print both values. And again, as a note, so for the brightness, we're measuring the average value among all the pixels that are within the surrounding of x plus radius, x minus radius, y plus radius, y minus radius. So within that area. Okay, so print star brightness and print star distance. Let's run it. Of course, distance is in parsec. Okay, we have an error here. Measure star average brightness. Okay, we need to go back to the function to check where the problem or the error is. So it is, the function is measure star maximum and average brightness. Both of them have this problem. Okay, so you see color in the conversion, we need to write color RGB to gray, okay, not BGR to gray. That's the error. So we compile them back, so to speak, both of the functions, although we're using only one, and we should have fixed it. So luminosity equal measure star average. Okay, so star brightness and star distance has already been fixed. Okay, so the star distance is 3.05 a parsec, with every parsec is around 2.38 light years. Okay, so luminosity equal measure star luminosity brightness. Okay. Brightness, okay, area equal measure star area. Print star luminosity equal luminosity. And the area is also in parsec around that. We run it, it should give us the correct values at last. Okay, and these values make a lot of sense.